Hello, I'm Mike McCulloch. Today I'd like to talk about why quantized inertia is a far better explanation for galaxy rotation than, dark matter, and exactly how quantized inertia predicts that galaxies stay bound despite their faster orbital speed. So I'd like to start with this diagram at the top of the first of the three. This shows a galaxy. So the round shape is a galaxy, could be the Milky Way, could be Andromeda, could be any disk galaxy. And on the right, I've shown a star in the outer edge, which is orbiting around very slowly. So there are two, well, we call them forces. Only one of them is a true force according to standard physics. There's the force of gravity inwards, which is shown by the leftward pointing arrow, and there's the centrifugal force, which is a pseudo force, which is pointing outwards. That's caused in standard physics because because objects like to travel in straight lines, and as the star is going round in its circle, it's always trying to go off in a straight line towards outer space. So it leads to a what appears to be a force outwards. In quantized inertia, this is a real force, but in standard physics, it's not. The trouble is they've observed that the outer stars of galaxies are orbiting far too fast, so that their centrifugal force should be much greater than the gravitational one pulling them in, given the amount of visible matter we can see in the galaxy. And you can see that with the difference in these two arrows, they don't balance. So standard physics predicts that all galaxies should explode or fly apart. But they don't. They're all nice and round, and they seem to be in balance. So what astronomers did was they added what's called dark matter to the galaxy, which is shown in the second picture. So here I've added a sort of dark halo of matter which can't be seen, but which increases the gravitational force. And you can see that the leftward arrow has been increased in length here to balance the large centrifugal force, so that everything goes in a balance. But of course, dark matter has not been seen, and it's deeply unpleasant as a scientific thesis because it's arbitrary. You just add it where the theory is deficient and fix the problem that way. It's a fudge. That's what it is. So, but it does produce a balance. So quantized inertia does things rather differently. So that's shown by the third schematic here. So here we have the star again, and we've got the gravitational force inwards from the visible matter only, so that's a leftward facing arrow. And then the way quantized inertia produces inertial mass is not by assuming that things just like to keep going in straight lines, which is not a real theory at all, but that inertia is a quantum force, a real quantum force. So here we have a star at the edge, which is accelerating towards the center. So the gravitational force is shown by the white arrow, but you can also consider that to be the acceleration of the star towards the center of the galaxy. And then a Rindler horizon forms in the opposite direction to the acceleration, which is shown by the black rectangle there, because information from out there can't catch up with the star because the star is accelerating away from it. So there's a horizon there. This means that Unruh waves that the star also sees, because it's accelerating, are damped near the horizon on the right-hand side, but Unruh waves can still exist on the left-hand side. So you can see the red wave there. So this Unruh radiation pushes the star out. It produces this centrifugal force, which in quantized inertia is a real quantum force caused by a mix of quantum mechanics and this horizon. The asymmetry produces, if the acceleration of the star is extremely slow, then the Unruh waves will be incredibly long and will start being disallowed by the cosmic size, by the cosmic scale. And so the red wave on the left will disappear and the inertial mass will decrease. And it turns out, when you work it out mathematically, that the inertial mass and therefore the centrifugal force decreases by exactly the amount required to balance the gravitational force from the visible matter only. So we get the red arrow on the right, which is much smaller than before and is exactly balances the gravitational force on the left. And so we have a nice balanced galaxy without the need for dark matter. So quantized inertia solves the galaxy rotation problem very elegantly and without any adjustment needed, which is good science. Okay, so I hope you've enjoyed this short, and I look forward to making another one tomorrow. Goodbye.